Yes. So, for couple of classes we were discussing about cycloaddition reactions, right. In that we were trying to understand Diels-Alder reactions, we covered them, and then we moved towards your Alder-Ene reaction. That was previous class we discussed about that. Today class what we are going to do is to take one more important reaction, that is your 1,3 dipolar cycloaddition, okay, which falls in your 4+2 cycloaddition reactions. Okay. So, we will start discussing 1,3 dipolar cycloaddition reactions. Yeah, I just shortly briefed you in yesterday's class about your 1,3 dipolar cycloaddition. I will just remind you one more time. So, what is that? You have an, you can take X minus, you can take a substrate, and then you have two substrates like this, fine. The reaction can be initiated if you have a double bond, okay, to give you a very nice 5-member ring. Okay. This so called beauty of your 1,3 dipolar cycloaddition. Normally, if you do your Diels-Alder reactions, you end up with your 6-member ring, right. In 1,3 dipolar cycloaddition, you end up with your 5-membered heterocyclic rings. Okay. So, you can think if you want to make 5-member heterocyclic compounds, I think 1,3 dipolar cycloaddition comes first in your mind, okay. And this reaction goes by heating. So, you are basically you have taken two substrates, okay, which on heating ended up giving you a 5-membered heterocyclic rings. Now, we will take we will try to understand all these substrates individually, okay, and the conditions, and then of course, we have to find out whether it is suprafacial or atrafacial, right. So, first we will take the substrates and try to understand how we call them. We have this X minus, Y plus, C. You have one this substrate, another you have this, okay. Basically, you call this as 1,3 dipole, okay, and this is if you want to see the similarity with your Diels-Alder reaction, this is your diene, okay, and this is your now 1,3 dipole, and this has your 5 pi electron system, 4 pi electron system. Fine. Now, you have an alkene here, right. In Diels-Alder reaction, you say this is your diene and this is your dienophile, but in this case, since it is a dipole, okay, since one of the substrate is dipole, you call them as dipolarophile, okay. This is your dipolarophile, and this was 2 pi electron system. And if you see the reaction, it is nothing but it is 4+2 cycloaddition based on Woodward-Hoffmann rule. Fine. Now, understanding more about your 1,3 dipolar and dipolarophile is very important to fix your dipolar cycloaddition reaction. You should know in detail how this 1,3 dipole looks and how your dipolarophile should be to understand your dipolar cycloaddition. So, what we will do is that now we will talk, we will put some focus on 1,3 dipole. if you take 1,3 dipoles, they can be broadly classified in two types. Okay, you can classify them in two types, 1,3 dipole. One you call them as allyl anion, one will be allyl anion type, another will be your Propargyl, or you can also call them as allyl anion. So, that is how you can broadly classify your 1,3 dipoles. One will be your allyl anion, another will be your Propargyl. If you want to see have their general structure, you can have an X minus, you will have Y plus. Fine. This can be in equilibrium. You can write other forms, not other resonance forms for this. You can write like this. For this you can write X minus Z plus, you can write for this X plus Z minus. So, you can write resonance structure for this allyl anion, and you can see they are dipoles, okay, 1,3 position. That is why we call them as a 1,3 dipole. Okay. So, what it says, it mostly says that this dipole can be nucleophilic as well as electrophilic, right. If you take allyl anion, so your Y can be, most of the time your Y can be nitrogen, oxygen or carbon, right, and your allyl anion will be bent in structure. If you see the structures, they will be bent in nature, okay, because they are sp2. When you look your Propargyl, in that case, Propargyl will be more like a linear, okay. You can have a Propargyl anion, which that will be more in linear in structure. Yeah, even I can write a nice resonance structure for them, X minus Y plus and Z plus Z minus S minus, again you have your linear structure, your Y can be your nitrogen. In this case, it will be linear. So, so that is how your 1,3 dipolar you can as two types, one allyl anion, another is Propargyl anion, and allyl anion, yeah, more like a bent structure, and your Propargyl anion is more like a linear structure. This is the two major type of your 1,3 dipole. Now, we will see there are many classification of allyl anions, and there are many good classification of your Propargyl anions. I will just take you some important classifications of allyl anions. Okay, done with it. Some main classifications which you see dipoles of allyl anion type. I am not taking to all the classification or many classification, I am just taking you towards some important classifications of allyl anions. Can you think about any? You have your nitrones, okay. Nitrones, they are very important type, which you can see many reactions of 1,3 dipolar additions taking place with nitron substrates, right. You can think about your carbonylides, right. have your carbonylides. Then you can even have your azomethionilides. And you have your ozone, right? Because ozonolysis, you know, ozone acts as a very good 1,3 dipolar cycloaddition ozone. Your nitro compounds, any other thing, azimines, because you have 3 nitrogens in azimines. You can even think about your azoxy compounds with 2 nitrogens. More like a bench structure, all are more bench structure. Okay, if I am linear, it is more like a bench structure. That is what allyl anion type is. So, you have other classes also, but these are like more important classes which you keep on seeing when you do reactions. Nitrones, you see many reactions with your nitrones. We are going to talk about nitrones, okay, and then we can talk about ozone, some reactions on some ylides and so on. But you can, these reactions are very common, which these are very common allyl anions which you see in 1,3 dipolar cycloaddition. So, then we will see some other classifications of Propargyl anion type, because that also we have to study on. Propargyl, or you can call as allyl anion type. Anything comes in your mind? Any compound? When I talk about Propargyl, nitrile oxides, because you can do many things with nitrile oxides. Many reactions you have studied with nitrile oxides. Then nitrile ylides, think about nitrile ylides, diazo alkanes, with 3 nitrogens. You have studied that, right? What is that? Azides, yeah, click chemistry. Because azides undergoes nice 1,3 dipolar cycloadditions. Very good example is your click. Then nitrous oxide. So, these are some main classification of your Propargyl anion type. So, what we will do is that we will take each type of allyl, 2 or 3 examples on allyl anion type, see how they do 1,3 dipolar cycloaddition. Same way we can take some examples of Propargyl and see how they undergoes cycloaddition reaction. Okay, fine. Okay. Now we will see like how we can comparison of 1,3 dipole and diene. Can you just like diene, we talk about more diene systems, right, when we talk about Diels-Alder reaction, and in this case it is more like 1,3-di. So, is there is any comparisons we can think about? Normally how your dienes are in Diels-Alder reaction, how the diene should be more like a nucleo, it should be nucleophilic, right? Fine, but in your 1,3 dipolar 1,3 dipole, how they should be? They are both, okay, they are 1,3 dipole are both electrophilic and nucleophilic. See, normal cases if you take dienes, okay, normally if you take dienes of in Diels-Alder reactions, what they use mostly diene systems, HOMO or LUMO. Yeah, normally you can see dienes, okay, will be having this HOMO for the reactions, but other way inverse electron demand you have seen, but otherwise dienes use most of the time HOMO, and you have seen you can use LUMO of your diene, okay, but it is inverse electron demand. In similarly 1,3 dipole also, okay, you HOMO or you can have LUMO depending upon your dipolar file. If you have an electron deficient dipolar file or you have an electron rich dipolar file, they try to change, okay, they sometimes you can use the HOMO, and other cases you will be using the LUMO. We will be seeing that in detail when it is going to use the HOMO and when it is do. Same way your dienes, see, like that you can try to understand both of them, okay, and both are 4 pi electron system, okay, you can count 4 pi electrons from your diene as well as your 1,3 dipole. Okay, this is more about your dipole, one of the substrate, okay. Then we will be talking about little bit about your dipolar file, okay. See, if you take a simple alkene, for example, I have taken simple alkene. Take a simple alkene, okay, how this, if it is if you take a simple alkene and do a Diels-Alder reaction, this is a good dienophile. Simple alkenes are not good dienophile, okay, but in 1,3 dipole, in the case of 1,3 dipole, they are very good, they are a good dipolar file. Okay, they are the, I can say they are bad dienophile, simple alkene, okay. Simple alkenes are good dipolar file, okay, that means you can do your 1,3 dipolar cycloaddition reactions with your simple alkenes, but it is not that good dienophile when you think about Diels-Alder reaction. See, if you are having a electron deficient alkene, if you have electron deficient alkenes, yeah, they are excellent, they in both the cases, they are excellent dipolar file as well as they can be a very good dienophile, right. That is fine, because it becomes a electron deficient. Yes, it can be act as a good dipolar file as well as it can be a good dienophile, but in the case of simple alkene, it is good dipolar file, but it is not good dienophile. That is about your dipolar file, okay. So, basically you want your dipolar file to be electron deficient if you want to carry out the reactions. So, that is about your 2 substrates, one your 1,3 dipole and another is about your dipolar file, clear. Now, what we will do is that this depending upon the HOMO and LUMO interactions, okay, your Diels-Alder reactions 1,3 cycloadditions, dipolar cycloadditions can be classified into 3 types, okay, depending upon the HOMO LUMO interaction, that is based on your FMO3. Just we will see how they are classified. Okay. How we can classify this 1,3 dipolar cycloaddition reactions using FMO3. Just have a case of, I will just have an energy here. Okay. So, I will take first case, or I will take one case where I have a dipole and I have an alkene system. So, this will be my this is the HOMO and this is the LUMO. Fine. This will be the HOMO of your dipole, 1,3 dipole, and this will be your alkene, the energy. If both are in the same, okay, energy, then we will be talking about the interactions of your HOMO of your dipole with the LUMO of your alkene, or otherwise we will be talking other way around if the energies are same. Okay. So, basically what you are talking, you will be HOMO of your dipole plus LUMO of alkene, or you can say HOMO of your alkene plus LUMO of dipole. So, you can think about 2 combinations here, right. This is one type. We can think of another type where the I have another case where I am going to have the LUMO and HOMO. Right. So, in this type we will be considering the HOMO of your dipole with the LUMO of your alkene. So, you do not have other case now. Okay. You cannot have your HOMO of your alkene with the LUMO of diene, that is possible is less. So, it will be HOMO of dipole with the LUMO of alkene or dipolarophile, right. So, same way you can think about other way around, right. That is, can have energy down still. The HOMO of dipole and LUMO, this is HOMO and. So, in this case what happens? You are talking about the HOMO of alkene with the LUMO of dipole. 1,3 dipole, fine. So, that means basically you have like 3 types, right. We are talking about 3 types now. This is your type 1, where you are talking about the interaction between the HOMO of dipole with your LUMO of your alkene. You have type 2, where you can have both the possibilities. In type 3, you are talking about the HOMO of your alkene with the LUMO of dipole, right. So, you have so that is how you can classify your 1,3 dipolar cycloaddition using FOMO3. We will see some example based on this, that will be much interesting, how this HOMO and LUMO you are talking about. Okay. That we will see some example. In that case you will understand. I will take you one example how you can talk with the HOMO and LUMO differently. For instance, we will take a nitron system. I take a nitron. Okay. One case I am taking nitron and reacting with an alkene. Okay. Same nitron I am taking another case. It is a similar nitron, same structure. Now, we have to think about this type 1, type 2 system, all these things, where it falls and how to understand them. Yeah. So, first point, what is this? This alkene, it is an electron rich alkene, right. So, if it is electron rich alkene, so it should be what? More nucleophilic, right. So, that means this is, see, basically try to understand, that means this is initiating the reaction. Okay, I can take this bond, fine. So, now you can think, so which will be the HOMO and which will be the LUMO, because this is initiating the reaction, because it is more nucleophilic. Okay. So, that means you are talking the HOMO about your dipolar file, okay. That is your alkene. Yeah. So, because this is in the HOMO and this will be your LUMO, that is how you classify it. See, if I again bring this O minus, it will do a cycloaddition, okay. But I do not want to do that, otherwise you do not know where it will be started, the whole reaction. Okay. When you take your second case, okay, it is an electron deficient alkene. So, it will be more electrophilic, right. So, then what I can think, the reaction this, right, this will be initiating. So, then I am talking about the HOMO of this and the LUMO of. So, that is why we say this dipolar file where is different from your diene, okay. Same dipolar file. Okay. Now, one case it acts as an nucleophilic, another case it acts as an electrophilic. Okay. It uses the LUMO, one case it uses the HOMO. Okay. It depends more about your dipolar file. If your dipolar file is electron rich, okay, then you are talking about the LUMO of your 1,3 dipole. If your dipolar file is electron deficient, then you are talking about the HOMO of your 1,3 dipole. So, that is why this classification of 1,3 dipolar cycloaddition is very important. Clear? In this case. Oh, sorry, I have read HOMO. Oh, yeah, it should be LUMO. So, thanks. Okay, if I take this classification again back, which we have done, if I take this classification, if I add Lewis acid, okay, then you know what will happen. The energy gap will become smaller and the reaction rate will be faster, just like your Diels-Alder reaction, just to remind you that point. Okay. That is more about your introduction about your 1,3 dipolar cycloaddition. So, basically you talked about your 1,3 dipole, it should be allyl type or it should be Propargyl type. Allyl type should be your bent one and your Propargyl will be linear. Then we slowly move to a dipolarophile. We said even simple alkene can do this 1,3 dipolar cycloadditions. And then we slowly moved the classification. We have seen 3 types based on their HOMO-LUMO interactions. Fine. So, that is more about that. Now, we will take individual dipoles and try to understand the chemistry of your dipolar cycloadditions. Okay. We will start with your famous dipole, that is your nitrones. So, nitrones will take in this case. First, we will try to do the synthesis of nitrones. Any idea how we can synthesize nitrones? See, if you want to synthesize, for example, I am giving this. I want to synthesize this nitron. You can take your simple aldehyde because it is sort of imine. You have to think more like an imine system. Okay. How to make the imine of this? Then you can get out. You can easily remove the hydrogen, so it can create an O minus. So, mostly if I have an OH here, then it will be more like an imine system, right. So, think in that. Now, what we can do if it is you want to create a imine, just you take an aldehyde, right, and treat it with your, I can think of my amine system. Okay. Then I can get my nicely get this. Okay. Then you can pull out your H plus. Can make like this your nitrones. Simple ways, very simple to make this nitrones. Another thing, there is another interesting nitrones which is your cyclic one, right, cyclic nitrones. We will see how to synthesize cyclic nitrones. See this type of can talk about this type of nitrones, cyclic nitrones. If you want to synthesize cyclic nitron, you can have your nice heterocyclic 5 member heterocyclic reactions. Can take N-ethyl. Just you have to make N oxide, you can use MCPBA, sorry, small m. If you take MCPBA, so you have your ethyl, just for you can create your O minus, right, N oxide, just MCPBA, N oxide you do. Then what happens, this O minus picks your H. So, your ethene can go out, giving an NOH, right. This, if you put in mercury oxide, you get your nice cyclic nitrones. Right, these are some synthesis of your like these are many ways. If you want to have your acyclic nitrones, you can synthesize them. You can synthesize cyclic nitrones. You can even there are many chiral cyclic nitrones and chiral acyclic nitrones you can synthesize. Okay. So, that is more fine. Now, before getting into this reactions, how this nitrones is going to react with your dipolar file, we should understand whether these additions are suprafacial or antrafacial, right. So, we will what we will do that we will see whether the HOMO-LUMO interaction and we will see how this reaction goes. HOMO-LUMO interaction between your dipolar 1,3 dipole and dipolar file. For example, I am taking a system where I have my NRO minus with a double bond, this type of system I am talking about nitron with my an alkene. So, how this addition should go, how this orbital should interact with each other. So, if I draw the, so we are talking about the HOMO of this with the LUMO of your alkene. So, it is the 1,3. So, can we draw the HOMO of this? It is more like your Allyl system. This is your oxygen, nitrogen, R. So, basically the node is on nitrogen now, because we are talking about. So, the node is on nitrogen, because we are talking about 1,3, right. So, now we will do, so this is your HOMO. So, now we will draw the LUMO of your dipolar file. Fine. So, you can see now the interactions more like a suprafacial. That is why this 1,3 dipolar cycloaddition reaction goes very nice when you do the thermal activation. Do a thermal activation suprafacially, it is allowed, just like your Diels-Alder reaction, it goes nicely. See, we said Diels-Alder reaction is nothing but how to represent them pi 4s plus pi 2s. But when you talk about ene reaction, it is more like a pi 2s plus pi 2s plus sigma 2s. Because in ene reaction you are talking about one sigma bond. So, it will be pi 2s plus pi 2s plus sigma 2s. Say if you want to talk about 1,3 dipolar addition, it is similar like your Diels-Alder, it is pi. So, it is pi 4s plus pi 2s cycloaddition. So, it is more like a suprafacial allowed. So, that is Now we'll see the reactions, how it gets. For example, I take a nitron, okay, and treat it with a system like 1. Okay. You have two systems like this. Now you have to carry out your I just heat it, thermally activate it. So what product you get? So this will be your dipole 1,3 dipole, and this is your dipolarophile. So just you have to attack your O minus, ne? So here, and then you have your thing here. So what you can think about just I can write here, so that I can O n. So when I fix my stereochemistry, this is the interesting part of this reaction. I can think about one product like this. Fine. Another product also which I can believe that so if it is R2, then this will be your R2 you are talking about. Yeah. Right. So you can think about two products now. If I take this nitron with your alkene system, which is an electron withdrawing one, electron deficient, okay, then I can think about these two products. See, if you carefully watch this product, one as we will see, but before that, one has been formed by endo approach and another has been formed by exo approach. Okay. What you studied in Diels-Alder reactions? Diels-Alder reaction, what it says? Which will be more preferable, exo or endo? In Diels-Alder, not here. In Diels-Alder reaction, we studied endo is more favorable. That is your endo rule, right? Endo rule says that endo product is more favorable compared to your exo, because in endo you will do see secondary orbital interaction. Okay. Can we use the same here? But if you see the product and if you find out the exo, okay, will be more favored when compared to endo. That means what I am trying to say is that your endo rule does not apply much here when you talk about 1,3 dipolar cycloaddition. It is more about your the product which is formed by less steric, that is in a less hindered way, is much more favored. Okay. So we will see why it is. Okay. Why it is endo rule is not, it is not favored here. Endo rule basically you cannot apply. You can say endo rule does not work. The way you look into it, you have to look less hindered products or less steric hindered products. Okay, is favored. See, that's very important when you look about your that we also people will say like exo endo adduct, exo endo adduct formation में when you particularly when you are talking about 1,3 dipolar cycloaddition reactions, your endo rule is not much obeyed. It's more about a less steric interaction. We'll see why it is. Okay. So if we take this and try to understand from the way of endo approach and exo approach, same reaction, we'll see how it is. We'll do an endo approach for this reaction. Okay. So we'll write for this the endo way. It's my R2O, my carbonyl, just for your understanding I am drawing double one bigger. Okay. So this might be my this is what, this is my dipolar file, right. Now my 1,3 dipole gets in, can have an hydrogen methyl and I have a methyl here, fine, which has a O minus. Fine, if you see this is the endo, it should come. Now if you see once the bond is formed, you can understand nicely. R2 I want to draw this nitrogen, then you have your hydrogen R. Okay. This is a nitrogen, you have a methyl. Now see in which side this N oxide is forming. Okay, this O oxygen, it's more exo, right, or endo, more endo way. Inside it's overlapping one. If you just open this structure, you see you will be getting a product just similar. I'm just, if you open, that's all, you doesn't know to do anything. This is your R1 I am talking about. So you end up with a endo product. Like your R1 is away, okay, in other plane, and you're talking about this N methyl. Fine. So you can see that by endo way this is, if you slow, now what you can do is that if you can slowly take it in the exo approach and see how it works. Same thing if you can draw in exo. Same way can you do it in exo. To have a carbonyl, nitrogen. Now I am doing the exo way, is left with my nitrogen, just flipping around. Now your O minus in this way, okay, and I have my methyl, just take the other way around, okay, and just for your endo opposite. Now, your O minus is in this way. So, if you write the structure now, hydrogen R CO2 R hydrogen methyl, talking about my nitrogen. So, this is the main part where you have to understand them. On oxygen now, okay. If you open this up, get this part. So, if you look the exo approach, okay, it is less steric in that, right. This O hydrogen, and if you see they are less steric in that. But if you take the endo approach, see in this case you have an methyl, okay. For example, I will take an endo approach, you have a methyl, but if I have a tertiary butyl type of system, okay, then you have a interaction more. So, in the exo case it is less steric, and that is why it is more favored, clear. So, what we will do is that in the next class we will see that now we said that by steric exo is much more favored. We will see that why endo rule is not applied here, what happened to your orbital interaction, why it is not favoring here, that we will see in the next class, okay. That is good. So, that is the end of this class.